So, in our earlier discussions on the MIPS 32 pipeline, we had basically concentrated on the integer instructions. We had seen how the pipeline works, we had seen the effects of the hazards, the interrupts and various ways to handle these problems and to improve the performance. But now, let us come to the real scenario. Well, in a real computer, we do not only have the integer operations or the instructions. We need also to process scientific data which are in the form of floating point numbers. So, we need floating point arithmetic, floating point processing to be done in the computer system itself. Now, so far we have assumed our EX stage, for example, will be able to finish a computation in a single cycle, but that is a little too optimistic. Realistically speaking, can you finish a multiplication or a division operation in one cycle? Well, you can, provided you make the clock sufficiently slow, but that is not a good idea. If you do that, everything else will also become slow, right. Moreover, we have seen that for floating point operations, you need multiple cycles to carry out the floating point operation itself, which means essentially your EX cycle itself may require multiple clocks. So, we are talking about something called multi-cycle operations. So, the topic of our lecture today is multi-cycle operation in MIPS 32. Let us see. As it said that the real implementation of the MIPS 32, where you can run all kinds of applications, they will contain obviously both integer and floating point units, and floating point operations are more complex than integer operations. Not only that, even within the integer operations, as I said, multiply and divide can be more complex than add and subtract. Okay. So, these kind of operations are slower in general and may require more than one cycle to finish during the EX stage. This obviously makes the pipeline scheduling and controlling much more complex, and we shall see more different interesting kinds of hazards can appear because of this. Because you see, earlier what you had assumed is that all instructions are of the same size, they take same time within 5 cycles, it is much simpler. But now when we say instructions can vary in time in terms of the execution, we are landing ourselves into a big trouble, right. So, which instruction will be finishing, maybe the earlier instruction will be finishing later, next instruction will be finishing earlier. Lots of such problems can occur. Okay. Let us see. So, the first and very naive solution is not to make any change in the control, just slow down the clock as I had said, such that your operation may be more time consuming, but you give sufficient time within a clock period to complete it. So, maybe earlier your clock was like this was your clock signal, but now you make the clock like this. Well, obviously this is not a good idea, because you are making your clock period slow means all your stages, not only EX, IF, ID, EX, MEM, WB, they will all be running at this speed t. Okay. So, if you slow down the clock, everything will slow down. So, that is not a good idea very clearly. Okay. This is the drawback, as I said, other operations are also slowed down, and this obviously will cause a severe degradation in performance, and obviously we cannot use it in practice. Let us see. So, what is the more practical solution? more practical solution is that we do not change or modify our instruction fetch, decode, mem and WB, because they do not change, they remain as it is. Our only concern is the EX operations, where the arithmetic operations are carried out, which here we are saying can vary in complexity. Our arithmetic operations are not of the same type, some are integer, some are floating point, even within integer they can be of various complexities. Okay, this is our concern. So, okay, let's assume integer and floating point for the time being. We allow floating point arithmetic pipeline to have a longer latency. So, logically speaking, what we are saying is that in the instruction execution cycle, the EX cycle is repeated more than one clock cycles. So, we are repeating the EX cycle several times, and how many times we are repeating, that depends on the complexity of the operation. All right. So, here as you shall see that in a real computing platform, if you allow this, the EX data path in the EX stage will actually be having multiple functional units, not just one. Maybe there will be one functional unit that will be handling addition or subtraction, there will be one functional unit for multiplication and one functional unit for division, right. Now, here there can be stalls due to structural hazards as well. You see, here there is a possibility of a stall if you are trying to issue an instruction, means your instruction is trying to move from ID to EX. It may so happen that the earlier instruction which was there in the pipeline, it was using the same functional unit and it was still somewhere in the EX. So, the next instruction cannot enter the EX unless the EX or the arithmetic is itself pipelined. You recall we discussed the pipeline implementation of some of the floating point operations. This is why we need that. If they are not pipelined, then while a previous instruction is doing multiplication, the next instruction has to wait for the multiplication until or unless the earlier one is complete. But if the multiply operation itself is pipelined, so when the first instruction is in the second stage of multiplication, the next instruction can enter the first stage. So, they can proceed in the overlapped fashion. Okay. So, if you have pipelining in the functional unit, then you can avoid structural hazard, otherwise there will be a structural hazard in the pipeline in the EX stage. Well, this is a logical picture where we are assuming that the EX stage, there are logically 4 functional units. The first one is our conventional integer unit, which you have seen earlier so far. So, for that the sequence will be IF, ID, EX, mem, WB. So, we are showing as the integer unit. So, the main integer unit will be handling all loads and store operations from memory, the integer ALU operations and also branches. There will be a floating point adder subtractor, another functional unit. This blue arrow indicates that you may have to iterate it several times. This is a multi-cycle EX stage. There can be a multiplier, floating point and also integer multiplier. I said integer multiplication can also take more than 1 cycles. So, this stage can do both floating point or integer multiply, and this is a division, floating point or integer division unit. So, as you can see, other than the integer EX unit, the other EX units are multi-cycle. They will need multiple cycles of EX. Now, earlier we had briefly looked at the MIPS 32 floating point registers and some of the instructions therein. So, just a quick recap. So, in the MIPS 32 there are 32 floating point registers which are named F0 to F31, they are all of 32 bit size. Well, when we work with double precision numbers, that means 64 bits, then we can take register pairs, that means there may even and odd register pairs like F0 and F1 you can take together, F2 and F3 and so on, and register pairs you name by the first one. F0 register pair means F0 and F1, F2 register pair means F2 and F3, similarly F30 means F30 and F31. So, like this you can use register pairs for double precision operations. Now, some examples I am giving here for such operations. Let us say the first instruction, L dot D means load double, D stands for double precision. Load double precision, you see this is loading from memory. So, whenever you are specifying the memory address, we are specifying the integer register 200 R2, which means memory 200 plus R2, and we are loading into F6 because it is double precision, it will be loading into F6 and also F7. This is R2 plus 200, this will be R2 plus 204, because memory is byte oriented and every register is 32 bits. So, 4 addresses per register. Similarly, store double, you store this F4 F5 into this memory location. So, F4 will get stored here, F5 will get stored here 44 plus 4. Similarly, you can have the other operations, all are double precision. Dot D means double. So, you write like this, that means F4 F5 and F6 F7 will be added, result will be in F0 F1 and similarly. Okay. So, we talk about latency and initiation intervals in this kind of multi-cycle pipelines. My multi-cycle arithmetic unit, whenever we talk about latency, what does the latency mean? You see, just as I mentioned that the arithmetic units are often pipelined wherever possible, because unless you do a pipeline you cannot overlap the operations. Like I am giving a small example, suppose there is one multiplication instruction followed by another multiplication instruction. Let us say I have an instruction fetch for this, instruction decode, then execute. This will take much longer, I am showing it like this, a much extended execute cycle, then mem, then WB. But for this one, well, you can do instruction fetch here, you can do instruction decode here, but you cannot start EX until this early instruction has finished it. So, you can start the EX cycle only here after this is finished, then mem. This is if it is not pipelined, but if it is pipelined, then your situation will be like this: instruction fetch, instruction decode. Let us say in the EX, let us say it takes 4 steps, let us say. So, there will be 4 cycles of EX, then mem and WB. So, for the second one you can do instruction fetch here, you can do instruction decode here, and it can start the EX from here itself, first step, second step, third step and fourth step. Okay. So, there is no need for any waiting, right. This is the idea, this is the idea of what I am saying. Fine. Now, latency means, now we are talking about the data dependencies. There is one instruction which is producing a result and another instruction which is using it. So, how many minimum number of clock cycles will be required between them? Like we had seen earlier that a load instruction followed by its use in an integer case required 1 stall cycles, which means latency was 1. Okay. But for floating point operations latency can be more. An initiation interval means how frequently we can issue instructions of the same type. Well, if it is fully pipelined, we can issue it every cycle, like the previous example of multiplication I have shown. Okay. These are the typical values which we will assume, and these values are very realistic. For integer operations which you saw earlier, latency was 0 and initiation operation was 1, because for integer ALU operations using data forwarding we could avoid all hazards, data hazards, and initiation interval it means 1 cycle we can apply the inputs. Memory followed data memory, there was a latency 1, there was a hazard we saw earlier, initiation interval was 1. For floating point add and subtract, we are assuming, see I am assuming that the number of EX stages in floating point add subtract is 4. So, between two consecutive means if there is a data dependency, the first instruction will be requiring 4 cycles to complete the add. So, the next instruction will have to wait for 3 more cycles, because anyway it is starting 1 cycle later, it has to wait 3 more cycles for this addition to complete, so that you can forward the result. Multiply requires 7 cycle, let us say, so the latency here will be 6. Okay. And we were assuming that the division unit is not pipelined and it takes 24 time units to run, that is why latency is 24, and initiation interval also is, no sorry, the total time taken is 25, that is why latency is 24, 1 less. This is not pipelined, because these are pipelined you can start one operation every clock cycle, but in divide, if there are 2 consecutive divides, the second divide can start only 25 clock cycles later, right. So, because these are the numbers, so you can have 4 floating point addition subtraction working together, 7 multiply operations working together, but only 1 division operation at a time, because it is not pipelined. So, our architecture looks like this. These are the pipeline stages, IFID, MEM and WB are here, these are the EX stages. So, integer unit has a single EX, for floating point addition there are 4 stages, for floating point multiplication there are 7 stages, and division is a single stage, but with delay of 25. So, it is a non pipelined, right. This is how a typical, you see division it is not pipelined mainly because, so well in some computers you will find division is also pipelined. There are 2 reasons. The cost of pipelining a divider is much more, only for very sophisticated number crunching computing platforms you need very fast division operations, there you can do it, but otherwise the frequency of division is much less as compared to other operations, addition, subtraction, multiplication. So, there are some RISC architectures where division is not pipelined. Okay. So, some interesting scenarios you can see here now. I have shown one multiply followed by an add, these are all double, load and store. Multiply will need 7 cycles in the execution stage, M1 to M7, add will require 4 cycles in the add stage, load and store will require 5 each total. Now, you see out of order completion of instructions, the third instruction finishes first, fourth instruction finishes next, then the second instruction, then the first instruction. So, for multi-cycle operation this is the first thing that happens. So, there will be out of order completion of instructions. Then second instruction illustrates some interesting read after write hazards. You see here the example I have taken is that a load which loads a double precision value in F8 and F9, then multiply which uses F8, deposits the result in F4, and add which uses F4, result in F6, and a store which stores F6. Let us see load will take 5 cycles like this, loaded value is available at the end of mem. So, with data forwarding, multiply operation can start only after the data is loaded after mem. So, there will be one stall cycle required. So, here multiplication can start. Now, add requires F4. Here again, even using data forwarding, F4 will be known only after multiplication is over here at the end of M7. So, add can issue, that means from ID to EX it can start only after that. There will be 6 stall cycles here. Similarly, add will finish here at the end of A4, but after A4 there is a mem stage anyway, and store will get its mem stage only after that, and store will happen here. So, there is no problem, store will take place here. So, there will be 3 additional stalls here. Okay. So, you can see that there are so many stalls because of RAW hazards in floating point operations. So, you see the number of stall cycles are significantly higher in these cases for multi-cycle operations. So, you need to take care, means the compiler needs to take care of this kind of things, and there are very sophisticated techniques which compilers use. Some of this we will discuss to prevent and try to fill up these slots for the stalls, delay slots. Okay. Fine. Now, another interesting example here, this results in a write after write hazards, which was never possible in an integer pipeline. See, there are 3 instructions I am showing: a multiply, a subtract, and a load, with 2 instructions in between. I am not interested in what instructions these are independent instructions, but the point is that they are all writing into some registers. Multiply will require 7 EX stages, subtract will require 4 EX stages, load will require 1. But interestingly, you see they all reach the WB stages together. So, there can be resource conflicts, structural hazard in the WB stage. First one is trying to write into F4, this one is trying to write into F6, this is trying to, this is also trying to write into F6. So, there is a conflict here, this needs to be handled. These instructions should not be allowed to reach WB stage at the same time. Okay. So, some stall cycles in WB also needs to be inserted here, but for mem in this example there is no conflict because only load is accessing memory, but here means although this instruction reach mem together, but here there is nothing to be done in mem for multiply and subtract, only WB, only this loads requires mem. Okay. The conflict in WB is important, here you need to insert stalls. Okay. So, with this we come to the end of this lecture, where see means we have not gone into detail, just we try to apprise you about the problems that arise in multi-cycle operations, what are the kind of issues and hazards that can show up, and of course, in a real machine there has to be a very sophisticated mechanism to handle all these kinds of problems. Okay. Thank you.